Hello friends, I welcome you in lecture number 6 on theory of probability. In this lecture we are going to discuss one important result which is known as Bayes theorem, and it is useful in calculation of conditional probabilities. And before understanding this Bayes theorem, first we will understand this result which is known as total probability rule, and we will use this result in the understanding of Bayes theorem. Now, to understand total probability rule, first I am considering three events denoted by B1, B2, B3, and I assume that these three events are mutually exclusive or they are disjoint events, and if we consider their union, then we get whole sample space. This means I have taken three events and these three events have no elements in common and their union is whole sample space. For example, this rectangle denotes the sample space S, and these three events are in such a way that there are no common elements and their union is whole sample space capital S. So this is meaning of mutually exclusive or disjoint events. B1 intersection B2 is empty, B1 intersection B3 is empty, and B2 intersection B3 is also empty. Now I consider one more event which is arbitrary event. Suppose I denote that event, arbitrary event, by capital A. So I am taking one more event, capital A, with the condition that its probability is non-zero. That means this event A occurs. Now we can observe that here B1, B2, B3 are mutually exclusive and they are intersecting with event A. So if we observe this part, then this portion is nothing but intersection of event A with B1. Similarly, if I consider this portion, then we can say that this part, I am not considering whole event B2, but I am considering this portion. This much portion is intersection of event A and event B2. Here also I specify that this much part is intersection of event A with B1. So this much portion is A intersection B1, and similarly if we consider this portion, this is intersection of event A with B3. So I denote this by A intersection B3. So these three events, A intersection B1, A intersection B2 and A intersection B3, these three events are also mutually exclusive or disjoint. We can see that there are no common elements for these three events. This is A intersection B1, this much part is A intersection B1, this is A intersection B2, and this is A intersection B3. So these events are also mutually exclusive, and they are mutually exclusive because this B1, B2, B3 are mutually exclusive. Now again, if we observe, if we take union of these three events, A intersection B1, A intersection B2 and A intersection B3, then we will obtain that union of these three events is event A. If I take union of A intersection B1, A intersection B2 and A intersection B3, then I will obtain event A. So now I am able to write this event A, whose probability is non-zero, as the union of three mutually exclusive or disjoint events. Now suppose I am interested in the probability of event A, then probability of event A will be equal to probability of union of these three events, which are A intersection B1, A intersection B2 and A intersection B3. So now I have probability of union of three events, and these three events are mutually exclusive. Therefore, by addition rule, we can write that probability of union of three events is equal to addition of probabilities of three events, because these three events are mutually exclusive. Okay, I am shortly writing as events are mutually exclusive or they are disjoint. So what I obtain that probability of event A is addition of probability of A intersection B1, probability of A intersection B2 and probability of A intersection B3. Therefore, probability of A is equal to, now I am using multiplication rule for probability. So using multiplication rule for probability, I can write probability of A intersection B1 as probability of B1 times conditional probability of A given B1. Similarly, using multiplication rule of probability again, this I can rewrite as probability of B2 times probability of A given B2, and similarly this we can rewrite as probability of B3 times probability of A given B3. Therefore, you can see we have obtained the formula for the probability of event A, which was arbitrary event whose probability is non-zero, and here B1, B2, B3 are mutually exclusive events, and this formula is known as rule of total probability or total probability rule. So in total probability rule or rule of total probability, we have three events B1, B2, B3 which are mutually exclusive and their union is whole sample space. So sometimes we will require rule of total probability to find out probability of this type of event A. Now this is for three events, and if we have n events denoted by B1, B2, Bn, then we can generalize this for n events also. Suppose we have n mutually exclusive events B1, B2, Bn, then this is equal to sigma probability of Bi times probability of A given Bi, where index I can take the values from 1 to n, and here we assume that all these B1, B2, Bn are mutually exclusive events and their union is the whole sample space. So this is total probability rule, and in total probability rule we have these conditional probabilities: probability of A given that B1 has occurred, conditional probability of A given that B2 has occurred, and conditional probability of A given that B3 has occurred. Now suppose we have this situation and we are interested in probability of B1 given that A has occurred. Here we are using probability of A given B1. Now I am taking reverse of this, that is conditional probability of B1 given that A has occurred. Then by the definition of conditional probability, this I can write as probability of intersection of two events, and I have to divide by probability of A. And now again I can replace this by using multiplication rule of probability. I have probability of B1 times probability of A given B1, and for probability of A I have by total probability rule, this is probability of Bi times probability of A given Bi, I equal to 1 to n. So in this way I can calculate conditional probability of B1 given that A has occurred. Similarly, if I am interested in the conditional probability of B2 given that A has occurred, then this I will replace by B2. So here if I am interested in the probability of B2 given A, then here I will have A intersection B2 divided by probability of A, and this by multiplication rule I can write as probability of B2 times probability of A given B2, and this remains as it is. So in this way we can in general write this formula also. Suppose I have n events B1, B2, Bn, then probability of Br given A, this is going to be probability of Br times probability of A given Br divided by probability of A, which is by total probability rule, probability of Bi times probability of A given Bi. I takes the values 1 to n, and here r can vary from r equal to 1 to up to n. So this formula is known as Bayes theorem. So we can use Bayes theorem to calculate conditional probabilities of this type. But here also we assume that all these events B1, B2 up to Bn are mutually exclusive and their union is the whole sample space. So I have written these two theorems or formulas here systematically. First I am writing that if B1, B2, Bn are mutually exclusive events of which one must occur, and if A is any event, then probability of A is given by sigma probability of Bi times probability of A given Bi. And because I have n events, I takes the values from 1 to n. This is rule of total probability, and this is Bayes theorem. Sometimes they ask you to write down the statement of Bayes theorem also. So for Bayes theorem also we will write that suppose we have n mutually exclusive events of which one must occur, and if A is any event, then conditional probability of Br given A is given by probability of Br times probability of A given Br divided by probability of A, and probability of A is given by rule of total probability or total probability rule. So now we understand these two formulas or use of these two formulas with the help of this example. In this example we have that a consulting firm rents cars from three agencies denoted by agency D, E and agency F. So they are taking cars on rent from three agencies, and they have given that 20% cars are rented from agency D, 20% cars are rented from agency E, and 60% cars are rented from agency F. Further, they are giving this information that if 10% of the cars from agency D, 12% of the cars from agency E, and 4% of the cars from agency F have bad tires. They are taking cars from different agencies on rent, and they find the percentage of cars from different agencies which are having bad tires. So this is the given information that a firm takes cars on rents from three agencies given by D, E and F, and percentage of cars from different agencies are 20% from agency D, 20% from agency E and 60% from agency F. These are the percentage of cars rented from these three different agencies. Then they are giving the percentage of cars with bad tires. So 10% of the cars from agency D have bad tires, then 12% of the cars from agency E have bad tires, and 4% of the cars from agency F have bad tires. This is given information, and using this information we have to find the probability that the firm will get a car with bad tires. In first part we have to find the probability that firm will get a car with bad tires. So how we will find out this probability? Probability that a car selected is with bad tires. So here we can see that if we take the total of these three, then it is 100%, 40 plus 60, that is 100. So we will consider mutually exclusive events B1, B2, B3 as car is taken from agency D or car is rented from agency D is denoted by B, car is rented from agency E will be denoted by E, or car is rented from agency F will be denoted by B3, or we can use D, E, F as the events that cars are rented from agency D, E and F. So let me check which notations I have taken. Okay, I have not written, so we can consider B1, B2, B3 as the events that cars are rented from agencies D, E and F. Let B1, B2, B3 denote the events that cars are rented from different agencies denoted by D, E and F. Now it is given that 20% cars are from agency D, therefore probability of B1 will be 20 by 100, that is 0.20. So first we write down that information. Given that 20% cars are from agency D, cars are from agency D is denoted by B1, so probability of B1 is 0.20. Similarly, it is given that 20% cars are from agency E, therefore probability of B2 is also 0.20, and 60% cars are rented from agency F, therefore probability of F is 0.60. Now we have to find the probability that the firm will get a car with bad tires. So we can denote the event that car is with bad tires by capital A. Let capital A denote the event that car is with bad tires, or car rented is with bad tires, and we have to find the probability of this event A. Now we are also given that if we know that car is having bad tires, then 10% cars are from agency D. So this 10% will help us to determine the probability that if car is with bad tires, then it has come from agency D. We are given that 10% of the cars from agency D have bad tires. That means first event occurred is B1. First we are considering that B1 has occurred, that is we are selecting or we are taking cars from agency D, and then we find that 10% are having bad tires from agency D. So probability of A given B1 is 0.10. Similarly, it is given that 12% cars from agency E have bad tires. So 0.12 will be the probability of A given B2. First we consider that car is rented from agency E, and then we find that car rented from agency E have 12% of the bad tires. Similarly, here first we have the event that car is rented from agency F, and then we find that 4% of the cars from agency F have bad tires, and this is 4%, that is 0.04. So that is given. So again we write given that probability that car with bad tires has come from agency D is 10%, that is 0.10. Then probability that car rented from agency E have bad tires is 12%, that is 0.12, and we are given that probability that car with bad tires is from agency F is 4%, that is 0.04. So now we are able to determine the probability that car with bad tires is, or probability that car randomly selected is having bad tires, or simply car with bad tires, and that we have denoted by event A. So this is equal to probability of A, and by total probability rule this we can rewrite as probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2 plus probability of B3 times probability of A given B3. And what we have applied, this is by rule of total probability or total probability rule. And now we are having all these values. Probability of B1 is 0.20, this is 0.10, this is 0.20, this is 0.12, and probability of B3 is 0.60, and this is 0.04. And by doing calculations with scientific calculator, I find that this probability is 0.068 up to 3 decimal places. So what I have obtained, probability that car with bad tires is 0.068. This is first part which we have answered using probability, total probability rule. In the second part we have to find the probability that a car with bad tires is rented from agency F. So here first event occurred is that a randomly selected car is selected and they find that it has bad tires, and we have to find the probability that a car with bad tires is rented from agency F, and car with bad tires from agency F is denoted by event B3. So here we have to obtain this probability. Car with bad tires, that is A has occurred first, and we have to find that it has been rented from agency F, that is probability of B3 given A. And to find out that probability we will use Bayes theorem. So now we write that car is rented from agency F given that car is with bad tires. This is what they have asked. They have asked that what is the probability that a car with bad tires has rented from agency F, and in our notations this becomes probability of B3 given A, and now we will use Bayes theorem. This is equal to, by Bayes theorem, probability of B3 times probability of A given B3 divided by probability of A. We have calculated probability of A here, and here I put value of probability of A, which is 0.068, probability of B3 is 0.60, and this is 0.04, and this I find as 0.353 up to 3 decimal places. And here I have to mention that this I have obtained using Bayes theorem. So whenever you have this type of problems in which you require this type of total probability or conditional probability, then you can use Bayes theorem, provided that you have conditions of Bayes theorem are satisfied. Here conditions are that we must have mutually exclusive events of which one must occur, and here we find that these three are mutually exclusive events, B1, B2 and B3. They cannot occur at the same time. Okay, they are considering cars on rent from agency F, agency E and agency D, and we can see that percentage of cars from different agencies is 100%, Therefore, we will consider B1, B2, B3 as mutually exclusive events for this problem, and then we consider car with bad tires as any event, and then we write down whatever is given in terms of notations of Bayes theorem, and we are able to solve this problem using total probability rule as well as Bayes theorem. So this is very easy result, and it is useful in calculating conditional probabilities for problems like this. So this is all about this session. I hope you like it. Thanks for watching.